Yeah, this is finally the last video of this course on the compiler. So thank you all for following up through here, and I really appreciate that you didn't drop already. And yeah, it's final session. Okay, so let's recap what we've done. So firstly, you've constructed your own optimizing C2RISC-V compiler, and I think it is kind of huge achievement for your career, and I really strongly recommend you to write it down on your resume so that your employer know that you implemented on optimizing C2RISC-V compiler. So it is a rare experience, I think, and I guess and I hope and it will raise your salary in the negotiation. Also, by doing so, by implementing an optimizing compiler, you've learned when to use a compiler basically. So compiler is necessary when you need programmability and efficiency at the same time. So it is for human who want a better programmability, and at the same time, it is for machine that is wanting to execute the instructions or programs very efficiently. And usually, these two virtues are 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 complementary. I mean, achieving. So, for example, when you use an assembly language, which is directly provided by the machines, then it is usually difficult to achieve programmability because it is too low level. But thanks to a compiler, you can work on a very high level language, C, C++, Rust, or other languages. You can achieve programmability, and at the same time, by using compiler, you can also achieve efficiency as well. So when you need programmability and efficiency at the same time in your programming, you usually use something like compiler. But that is almost always, almost always when you do a project, you want programmability and efficiency at the same time. So probably you need a compiler almost always. And you've also learned that the basic principle behind compiler that enables a compiler to be used when in such a case is that it is basically an engineering of abstraction. So compilers translate a higher level abstraction to low level abstraction. The in For this course's context, the higher level abstraction should have been the C program language, and the lower level abstraction should have been the RISC-V assembly language. But it happens in other contexts as well. You probably want to compile your Rust program into assembly, or your JavaScript program into assembly, and etc. etc. And it is a small view. In a bigger viewpoint, you can think of everything is a compiler. For example, your UI toolkit is a compiler that translates the human interaction into the intention of the program. Or your library can be thought of as a compiler that translates a higher level interface into a low level working or low level implementation of the library. So it is a little bit pedantic view, but you can think of everything as a compiler or abstraction engineering. So in this viewpoint, this viewpoint is probably one of the most important thing you can learn from this compiler course. Everything can be thought of as a compiler, and this viewpoint will improve your ability to write, for example, a UI library or some other framework, or for example, a web framework, or etc. Okay, so in this course we dealt with a very basic C2RISC-V assembly compiler, and if you are still interested in compiler, you may want to continue to study other subjects of compiler as well. For example, you'd like to see how the mainstream compilers are organized. You can look into the GCC's or LLVM's code base and what's going on there. So both of the projects are about several million lines of code project. So it is a huge project, and you can start on a small portion of that. That is probably understandable, uh, and yeah, and quite easily reachable once you study this course. So I recommend you to do that. So furthermore, if you want to write a compiler for your own small language, which can be necessary in your career, then you can consider using GCC or LLVM as your backend compiler. You can just implement a front end, and the backend will deal with all the optimizations that is discussed in this course and more. Furthermore, you may want to know how to compile more advanced programming techniques like object-oriented programming or functional programming. So this poses different challenges than just compiling C compilers. For example, in object-oriented programming, you need to track the type of this object in runtime. You need to annotate each object with its runtime type. So how to do that? So you may already heard of the vtable or vptr, which is a strategy used in C++ compiler to implement the OP hierarchy. And you need to deal with the first class functions in functional programs. How to express a function as a value inside a machine. So also, again, it is implemented as a pointer to a function, but in addition to that, you usually need to annotate the function pointer with the context of the function. So if you already know what is called closure, you probably learned it from the programming languages course. You need to remember the context values that is captured inside the function. So in order to track the captured values, you need to somehow annotate a function pointer with a pointer to the context or pointer to the captured variables. So such a detail should be discussed when you need to implement a compiler for OP or functional programming languages. So, and furthermore, you may want to know in what sense a compiler is correct and how to prove that a compiler is correct. So we dealt with the optimizations and we discussed the motivations behind it. For example, the death code eliminations motivation is removing redundant computations, but we didn't discuss very well about why these optimizations are correct. And in order to make sure that an optimization is correct, you first need to define the formal semantics of programming languages, which we tried in a session, but we didn't discuss very well. We didn't discuss in very detail. And probably you may want to know how to precisely define the formal semantics and how to precisely prove or formally verify a compiler correctness. So it is probably the next topic. And actually it is one of the most important topic in my PhD thesis. So if you're interested, please refer to my PhD thesis. And you may also want to know how to construct a just-in-time compiler or a JIT compiler. So as discussed in the first lecture, a JavaScript program, for example, should be compiled and executed at the same time. And in such a case, we can further optimize the execution of the programs. We first compile a JavaScript program very naively, and only later you can work on optimization after collecting some program data. For example, if your program doesn't enter a loop, then you can safely ignore the loop at all. Or if you are entering a loop very often, you want to optimize the loop body as much as possible. And you can decide that on runtime instead of the compile time because you're compiling and executing at the same time. So only if a loop is very hot, you're going to optimize it very diligently and do it. Furthermore, you may want to construct a compiler for the emerging workloads like AI or machine learning. For example, how to construct a compiler for TensorFlow representation of deep learning models or PyTorch into some accelerators like GPUs, TPUs, or the emerging architectures like NPUs from the Furious AI of the invited talk, etc. Okay, these two topics, just-in-time compilers and compilers for machine learning, are, I think, the most important next topics in the field of compilers. And these compilers topics are not only limited to compiler people, but almost all industry are interested, all systems programming industry are interested in this compiler construction. So I hope that what you've learned so far is very beneficial for your career. Okay, and now lastly, you may want to join the my laboratory, the concurrency and parallelism laboratory, and we are trying to optimize the existing concurrent and parallel systems, and at the same time, we want to make sure that they are safe. So we are trying to achieve safety and performance at the same time by understanding the principles of concurrency and parallelism. And in order to do so, we are very good at engineering abstractions for systems programming. So as I said, a compiler is basically abstraction engineering. So in this viewpoint, we are trying to engineer abstractions for systems programming. For example, what is context switch? What is operating systems? And what is memory subsystems? What is a good abstraction or good intermediate representation for machine learning workloads or JavaScript workloads, etc. Or how to construct very high performance networking systems, how to construct abstractions that doesn't lose the performance of the underlying hardware, and at the same time, it is good. It has good programmability for programmers to write program easily. So finding such an abstraction for example, networking systems is the first step towards very flexible and yet very performant networking systems. So we are doing such a things, engineering abstractions for systems programming. So if you're interested, please apply for the summer internship. And this link will point to a Facebook post in the KAIST SOC group that explains how to apply for internship and what better describes what you are doing in this laboratory. Okay, so that is pretty much everything I have prepared for this course. And I really hope that you enjoy this course a lot. I know that it was a very demanding course. It is the first time I teach compiler, and you probably have no 족보 or everything. So I know that you have struggled very far. And I promise you that I can give you quite decent grades as far as you at least finish one of the homework. So I promise that if you finish at least one of the homework, you will not get F. So I promise that. And please enjoy your homework, and I hope most of you finish all the homework at the end of the semester. And thank you for attending this course. Bye bye.